Biscuit Basin, Yellowstone National Park, June 13, 2026. Early morning. The area around Black Diamond Pool has been under enhanced monitoring since July 23, 2024, when a hydrothermal explosion at the same location destroyed the tourist boardwalk, created a new crater roughly 200 feet across, and scattered debris across the area without warning and without precursory signals. A webcam was installed on the remaining boardwalk in May 2025 and has been watching the pool continuously ever since. At 5:09 a.m. Mountain Daylight Time, the webcam captures something. A dark-colored steam plume jets from the ground just north of Black Diamond Pool. Not from the pool itself, from the barren ground nearby. Monitoring equipment registers seismic energy and infrasound simultaneously. New water-filled fractures open in the earth to the north of the pool. The Firehole River, 5 kilometers downstream, turns milky gray as hydrothermal water and sediment surge in from 3 newly formed vents. Later that morning, park staff noticed the river stays that color for hours. It is the 5th hydrothermal explosion at this specific location in 2026 alone. No one was hurt. No one was nearby. The area has been closed to visitors since July 2024, partly for safety reasons, partly because the webcam and sensor network installed after the original explosion make better scientific observations without people in tee frame. The USGS logs the event, documents the new fractures, and updates the monthly Yellowstone Volcano Observatory report. The alert level remains at normal. The aviation color code remains green. No change in volcanic hazard assessment. And yet, in the months before this explosion, 3 developments have come together at Yellowstone that are, taken individually, each interesting. Taken together, they represent the sharpest revision in the scientific understanding of what Yellowstone Act 2 ally is that the field has seen in years. The first, a machine learning algorithm applied to 15 years of Yellowstone seismic recordings, found 86, 276 earthquakes that human analysts had never cataloged. The system beneath Yellowstone is roughly 10 times more seismically active than the cataloged T-hat scientists had been working from suggested. The second, a research team from the Institute of Geology and Geophysics of the Chinese Academy of Sciences, using the most complete 3-dimensional model of the Western North American mantle ever constructed, published a paper in Science in April 2026. Concluding that Yellowstone's magma does not come primarily from a deep mantle plume, as the standard model has assumed for decades. It comes from much shallower sources, driven by horizontal flow from the remnants of the Farallon Plate, processed through a system of crustal reservoirs in ways the old model did not capture. The third, beginning in July 2025, a section of the North Caldera Rim began to uplift, in the same location where the last major deformation episode of 1996 to 2004 had occurred. The uplift stopped in January 2026, without the subsidence that usually follow such episodes, leaving a deformation pattern that USGS scientists explicitly described as having no clear outcome prediction. None of these 3 things means Yellowstone is about to erupt. The USGS is direct about this, as they always are. The system is at background levels. The volcano is not building toward an eruption. But what these 3 things mean, taken together, is something that scientists are more careful about saying publicly. The system they have been monitoring for decades is considerably more complex, considerably more active at scales below previous detectio and limits, and considerably less well understood in its fundamental driving mechanisms than the standard account of Yellowstone suggested. And understanding something less well than you thought you did is, in a system of this scale, a legitimate reason to pay very careful attention. There is a difference between a volcanic system that is dangerous and a volcanic system that is surprising. Yellowstone is not, by any current assessment, about to erupt. The USGS has been monitoring it for decades. The magma chamber beneath the caldera is 5 to 15% molten, mostly solid crystal mush. The annual probability of a supereruption is approximate, Li 1 in 1730, 00. None of the monitoring signals that would precede a significant eruption, sustained large-scale seismic swarms, major ground deformation measured in meters rather than centimeters, dramatic changes in gas output, are present. What has happened in the past 12 months is different, not threatening, surprising. 3 separate scientific developments, each from a different methodological direction, have each found something at Yellowstone that does not fit the standard picture. Together, they suggest that the model scientists have been using to understand one of the most closely watched geological systems in the world needs significant revision. And when the model needs revision, the things the old model was used to predict become less certain. That is what gives volcanologists pause. Not imminent eruption, incomplete understanding. This video is about 3 new Yellowstone findings from 2025 and 2026. What each one reveals on its own, and what they collectively suggest about the state of scientific understanding of this system. The first is the AI Seismic Catalog, published in Science Advances in July 2025. 86, 276 earthquakes identified in 15 years of Yellowstone data that human analysis had missed, with over half forming swarm-like clusters linked to underground fluid movement, revealing a system roughly 10 times more seismically active than the working catalog suggested. The second is the April 2026 science paper on Yellowstone's magma origin, a 3-dimensional model of the western North American mantle that concludes the magma feeding Yellowstone's volcanic system comes primarily from shallow asthenospheric sources. Dr. Ivan, by an eastward horizontal mantle wind, from the subducting Farallon plate, rather than from the deep mantle plume that has been central to the standard model for decades. The third is the July 2025 to January 2026 North Caldera Rim uplift, a deformation episode in the same location as the 1996 to 2004 episode, which ended without the expected subsidence, producing a deformation state that us scientists explicitly describe as having no clear prediction for where it leads next. And running through all 3. The June 13, 2026 hydrothermal explosion at Biscuit Basin, the 5th at that location in 2026, in an area that has now had 2 major hydrothermal events in less than 2 years. By the end of this video, you will understand what each of these findings actually showed, why they matter individually and collectively, and why the honest scientific response to them is not alarm, but a specific kind of attentiveness that comes from recognizing that a system is less understood than previously believed. What did the AI seismic analysis find that human analysts had missed? And what does 10 times more earthquakes than previously cataloged tell us about what is happening beneath the Yellowstone caldera? How does the new mantle model change the understanding of where Yellowstone's volcanic power comes from? And why does the distinction between a deep plume origin and a shallow asthenospheric origin, driven by horizontal mantle flow, matter for how the system behaves? What is happening at the North Caldera Rim? And why did the uplift stopping without expected subsidence produce an observation that us scientists describe as having no clear outcome prediction? Why has Biscuit Basin now experienced 5 hydrothermal explosions in 2026? And what does the pattern of activity at Black Diamond Pool suggest about the hydrothermal system's current state? And what does it mean, practically and scientifically, when 3 independent lines of research all find that a well-monitored system is more complex and less understood than the existing model described? This is not a video claiming Yellowstone is about to erupt. The USGS alert level is normal. The volcanic hazard assessment has not changed. No monitoring signal associated with magmatic ascent toward the surface has been detected. These facts are not being softened or glossed over in this video. They are the anchor. What this video is about is something more specific and more interesting than the standard "Is Yellowstone going to erupt?" question. It is about what happens when 3 independent scientific programs, using 3 different methodologies, all return findings that require the model of a well-studied system to be revised. Not scrapped, revised. In ways that make some things previously considered understood genuinely uncertain. The reason volcanologists pay attention when this happens is not that uncertainty automatically implies danger. It is that managing any geological hazard requires an accurate model of the system. If the model is incomplete in specific identified ways, the parts of the hazard assessment that depended on those parts of the model need to be re-examined. That re-examination is what is happening at Yellowstone right now. This video explains what triggered it. Before we go further, if you want science told at the level where the actual new findings are explained rather than just labeled alarming or debunked, subscribe to Galaxy Pulse. Now, back to Yellowstone, and to the 3 things that have surprised scientists who have been watching it for decades. The Yellowstone Volcano Observatory has been in continuous operation since 2001, integrating data from approximately 50 seismometers, more than 15 GPS deformation stations, gas sensors, infrasound instruments, and satellite-based thermal imaging. Monthly reports are published for every month. The data is publicly accessible. By any measure, Yellowstone is among the most intensively monitored geological systems in the world. The standard model that decades of this monitoring has produced describes Yellowstone as a volcanic system in a quiescent phase between major eruptions. The magma chamber beneath the caldera, imaged by seismic tomography, is mostly solid, roughly 5 to 15% melt fraction, a crystalline mush rather than a reservoir of liquid rock ready to erupt. The caldera breathes, inflating and deflating as magma and hydrothermal fluids shift in the crust at rates of centimeters per year. The seismicity is persistent and distributed, averaging 1/500 to 2/500 located earthquakes per year in the USGS catalog, mostly microearthquakes below magnitude 2. To understand the scale of what is being monitored, the Yellowstone caldera is approximately 72 kilometers long and 55 kilometers wide, roughly the footprint of a large American city, and was formed by the collapse of the ground surface into the emptied magma chamber following the last supereruption, 1640 years ago. Beneath this collapsed landscape sits a magma reservoir at depths of 5 to 17 kilometers, fed from below by the mantle. Above the magma system, a vast hydrothermal system, water heated by sea contact with hot rock and circulating through fractures in the crust, produces the geysers, hot springs, fumaroles, and mudpots that make Yellowstone geologically unique. It is this hydrothermal system, not the magma itself, that is most directly relevant to the hazards that visitors to the park face. Hydrothermal explosions, which have occurred throughout Yellowstone's history and continue to occur, can happen without warning and without any connection to volcanic eruption. The standard account of what drives this system is the Yellowstone hotspot, a mantle plume rising from deep in the mantle, possibly from near the core mantle boundary. which has been moving northeast relative to the North American plate for approximately 17 million years, leaving a chain of calderas across what is now the Snake River Plain before arriving at its current position beneath Wyoming. The hotspot model explains the geographic distribution of the volcanic field, the chemical character of the erupt-ed material, and the connection between Yellowstone and the broader volcanic province of the western United States. It also faces a specific problem that has been contested in the scientific literature for years. Direct, seismic imaging of the mantle beneath Yellowstone has, over the years, produced ambiguous results about how deep the plume actually extends. Some studies see it descending into the lower mantle, others see it only in the upper mantle. Whether Yellowstone is driven by a true deep plume from near the core mantle boundary, or by something shallower and structurally different, has been an open question. The April 2026 science paper addresses this contested question with the most comprehensive dataset and most detailed model yet constructed. The April 2026 magma origin finding under the standard model. Yellowstone's activity is driven from deep below, with a plume rising through thousands of kilometers of mantle, providing the thermal anomaly that powers the volcanic system at the surface. In this picture, the system is connected to Earth's deep interior in a way that makes it powerful, long-lived, and geographically stable as the plate moves over the stationary heat source. The April 2026 paper, published in Science, challenges this picture at a fundamental level. Lead author, Zebin Cao and colleagues at the Institute of Geology and Geophysics of the Chinese Academy of Sciences constructed a three-dimensional geodynamic model of the entire western North American mantle, combining seismic imaging data, electrical conductivity measurements, and geodynamic simulations in a unified framework. The paper's title captures its central claim: tectonic origin of Yellowstone's translithospheric magma plumbing system. The DOI is 10/26/Science. ADI 2/27. Their conclusion is that most of Yellowstone's magma originates from the shallow asthenosphere, the upper portion of the mantle sitting just below the rigid outer crust, with little contribution from a deep plume. The mechanism is not a column of hot material rising from the deep earth, but something more lateral. An eastward mantle wind, driven by the subduction of the ancient Farallon Plate, whose remnants lie deep beneath central and eastern North America. This horizontal flow of hot asthenospheric rock K is carried toward the Yellowstone region, where it encounters the thick overlying lithosphere and is pushed downward. The compression and extension from this interaction create decompression melting, the same process that produces magma at mid-ocean ridges, generating the melt that eventually works its way up through a tilted, southwest dipping network of fractures in the lithosphere to feed Yellowstone's volcanic system. The model identifies a translithospheric magma plumbing system, a connected pathway from the shallow mantle through the rigid plate that is primarily controlled by the mechanics of the overlying crust and the regional tectonic setting, not by heat risen G from the deep earth. This is a significant revision, not a complete abandonment of the hotspot concept, but a fundamental recharacterization of where the energy and material come from that powers Yellowstone. The Cao et al. Paper's authors note that these findings likely apply to other volcanic regions as well, suggesting that shallow asthenospheric sources controlled by tectonic extension may be a more general mechanism for large volcanic systems than the deep plume model has implied. Why does this matter for hazard assessment? The deep plume model predicts a relatively continuous and stable supply of material from depth, making the long-term magmatic output of the system relatively predictable. The shallow, asthenospheric model predicts something more episodic and tectonically controlled. A supply that is more sensitive to changes in regional stress and structural configuration. If this is correct, the timescales and patterns of magma supply to Yellowstone's crustal reservoirs may be more variable than the standard model assumed. The most concretely surprising of the three new findings is the machine learning seismic catalog, published in Science Advances on July 18, 2025. The study was led by Manuel A. Flores, with co-authors including Bing Lai, an engineering professor at Western University in Canada, whose lab contributed significantly to the work, along with David R. Shelley of the USGS, of Angulo, and José D. Sanabria A. Gómez from the Universidad Industrial de Santander in Colombia. They applied deep learning algorithms, specifically the EQ transformer and phase-link tools, to 15 years of raw seismic waveform data from the Yellowstone caldera, covering the period from 2008 to 2022. The approach generated more than 7 million high-confidence phase picks from continuous waveforms, compressional and shear wave arrivals that human analysts had not individually identified. The goal was not to find new phenomena. It was to find earthquakes that human analysts had missed in the existing data. Before machine learning, earthquake detection at Yellowstone followed the standard process. Trained analysts examined waveform data looking for the characteristic signatures of seismic events. This method works well for earthquakes of magnitude 2 and above, which produce clear signals. For smaller events, the signal-to-noise ratio is lower, and the task of identifying individual earthquakes among continuous background noise becomes progressively harder and more time-consuming. The practical detection threshold, LD, of the human-analyzed Yellowstone catalog was approximately magnitude 1 to 1.5 for most of the monitoring period. Below this threshold, earthquakes were known to be occurring but were not individually cataloged. The catalog said approximately 7,000 to 8,000 earthquakes per year in the Yellowstone region. What it did not say was how many smaller events were happening fell below the detection threshold. When the machine learning analysis was complete, the catalog for the 15-year period contained 276 earthquakes, approximately 10 times the number in the human-analyzed catalog for the same period. Lai described the significance in a statement. Before, we could only indirectly measure space and time between events, but now, we have a far more robust catalog of seismic activity under the Yellowstone caldera, and we can apply statistical methods that help us quantify and find new swarms that we haven't seen before, study them, and see what we can learn from them. The specific character of the newly cataloged earthquakes matters scientifically in multiple ways. Over half formed part of swarm-like clusters, bursts of seismicity with no clear main shock, often linked to underground fluid movement. The paper also found that adjacent earthquake swarms, separated by long quiescent periods, are a dominant feature. Meaning, the hydrothermal system does not move fluidly and continuously through the crust, but rather builds pressure, breaks through a permeability seal in episodic injections, and then quiets down before the next episode. A second finding from the catalog concerns the geometry of the fault structures hosting these swarms. The Flores et al. Paper characterized earthquake source properties by modeling them as fractals, geometric shapes that exhibit self-similarity, appearing similar at different scales. Fractal analysis of earthquake fault surfaces gives a measure of their roughness versus smoothness. What the analysis found is that the fault structures beneath the Yellowstone caldera are rougher and less mature than the faults typically seen in regions like Southern California or even immediately outside the caldera. This roughness tells seismologists something about the geological age and history of the fault network. Smoother faults have been ground down by years of slip. While rougher faults are younger, less developed, still in the process of being worn in. The fault network within the caldera itself is geologically young and still evolving, which is physically consistent with a caldera system that has been repeatedly rem-a-day by volcanic activity. From the perspective of hazard assessment, the catalog expansion enables a type of analysis that was previously impossible: statistical characterization of swarm behavior. With 276 events over 15 years, it becomes possible to establish what a typical SW arm looks like at Yellowstone, how long it lasts, how many earthquakes it contains, where it occurs, and how its characteristics vary across the caldera. This statistical picture can then be used to identify when a new swarm deviates significantly from the baseline, potentially an important tool for real-time hazard monitoring. Three concepts are essential for understanding what these findings actually mean. The first is the distinction between detecting earthquakes and understanding them. The AI catalog finding does not mean Yellowstone suddenly became more seismically active in July. Earthquakes were always happening. What changed is the ability to find them in the archived data. The system is not more active than it was, but it is more active than the previous catalog showed it to be, which means the model of the system was based on an incomplete dataset. The second is the significance of swarm-dominated seismicity. A traditional earthquake sequence has a main shock followed by aftershocks decreasing in size over time. A swarm has many earthquakes of similar size without a clear main shock, occurring over days to weeks. Swarms at volcanic and hydrothermal systems are often driven by fluid movement. Pressurized fluid, forcing its way through cracks in the rock, creates seismicity distributed along the path of the fluid. The dominance of swarm-type seismicity in the new catalog, over half of all events, is consistent with Yellowstone's known character as a hydrothermal system, but is now confirmed at an order of magnitude finer resolution. The paper's specific finding, that swarms involve both slowly diffusing aqueous fluids and rapid episodic fluid injections from breaking permeability seals, is a more detailed physical picture than was available before. The third is what the North Caldera Rim uplift episode means in context. The North Caldera Rim area began uplifting in July 2025, in the same location where uplift had occurred during 1996, and continued into 2013 to 2014, when uplift near Norris Geyser Basin occurred at rates of up to 15 centimeters per year, one of the fastest deformation rates ever recorded at Yellowstone. That episode ended with the M4.8 earthquake of March 2014 and rapid subsidence. Chief seismologist Jamie Farrell explicitly noted the parallel in a Caldera Chronicles article, while also noting that a seismic swarm occurred directly on the center of uplift in November 2025. The uplift stopped in January 2026, without the subsidence that followed the previous episodes. Where this leads, Farrell wrote, is unclear. At this point, there is no way of knowing what will come of this current deformation episode. Here is why the convergence of these three findings matters beyond the specifics of each. The Yellowstone Volcano Observatory manages a volcanic hazard assessment that informs everything from national park visitor safety protocols to federal emergency planning. That assessment is a model-based product. It uses the best available science about what is happening beneath Yellowstone, how the system works, and what precursory signals would indicate elevated risk, to produce a characterization of the current hazard level. When the model is revised in significant ways, the assessment built on that model must be revisited. Not necessarily changed, but revisited. Does the new understanding of magma origin from shallow asthenosphere, rather than deep plume, change what the Manito ring should look for? Does the expanded seismic catalog from AI analysis change the threshold at which a seismic swarm should be considered potentially anomalous? Does the unexplained deformation pattern at the North Caldera Rim, which does not fit the historical precedents cleanly, require monitoring resources to be redeployed? These are the questions that the three new findings put on the table for the USGS and the broader scientific community. Not whether Yellowstone is about to erupt. The answer to that question has not changed. But what monitoring is needed, what data is needed, and what baseline the data is being compared against. Those things have been meaningfully complicated by a year of scientific findings that each, from a different direction, show the standard model to be incomplete. Farrell's own words capture the situation honestly. There are no clear answers at this point. YVO scientists will keep monitoring this deformation and the associated seismicity. That is not alarm. That is honest science, in a situation where the data does not yet have a clear interpretation. The three findings described so far, the AI earthquake catalog, the new magma origin model, and the unexplained North Caldera Rim deformation, represent surprises from outside the standard monitoring program, AI analysis of historical data, a comprehensive new mantle model, geodetic observations that don't fit the historical pattern cleanly. But there is one more thread, closer to the surface and more immediately observable. The hydrothermal system itself, in 2026, is producing events that the monitoring infrastructure installed after the 2024 Biscuit Basin explosion was specifically designed to detect. 5 hydrothermal explosions at Biscuit Basin so far in 2026. The June 13 explosion, creating new fractures, new vents, and a new pool that was forming via collapse between June 14 and 16, spouting boiling water 6 to 9 meters into the air by June 18. The new monitoring network is doing exactly what it was installed to do, capturing events in real time that would previously have gone unrecorded. The USGS Caldera Chronicles article on the June 13 event noted that it occurred about 100 meters from the new Biscuit Basin monitoring station, and that no hydrothermal explosion has ever occurred this close to a monitoring station, calling it an unprecedented opportunity to study hydrothermal explosion precursors. Whether the frequency of these events reprise, NTS, a change in hydrothermal system behavior, or simply better documentation of activity that was always occurring, is one of the specific open questions the new monitoring is designed to eventually answer. The details, the debates, and the full picture. The 86-76 earthquake catalog is not simply a bigger version of the existing catalog. It is qualitatively different from the human-analyzed catalog in ways that open new scientific questions. The spatial distribution of the newly detected earthquakes reveals structure in the subsurface that the previous catalog hinted at, but did not resolve clearly. The high density of events in specific locations and their spatial clustering into swarms allows, for the first time, a direct, statistical analysis of how fluid-driven seismicity is distributed through the caldera's crust at small scales. The correlation between swarm locations and known hydrothermal features, including the Norris Geyser Basin and Teehee Biscuit Basin area, is now documentable in much more detail than before. A key physical insight from the Flores et al. Analysis is the mechanism behind swarm sequences. The paper proposes that swarms at Yellowstone are controlled by the interplay between two processes. slowly diffusing aqueous fluids, moving through permeable rho CK over long timescales, and rapid episodic injections of fluid that occur when built-up pressure breaks through a permeability seal, a layer of less permeable rock that has been restricting fluid flow. The breaking of the seal creates a burst of seismicity. The swarm. After the seal breaks and pressure equalizes, seismicity quiets. Then the slow diffusion process gradually rebuilds pressure until the next seal breaks. This picture of the hydrothermal system as a collection of pressured compartments separated by permeability seals, periodically rupturing and resealing, is new. It was not visible in the sparse human-analyzed catalog, but emerges clearly from the 86-76 event dataset. The temporal patterns in the new catalog also carry information. Adjacent swarms, separated by long quiescent periods, are connected, meaning that fluid moving through the crust links swarm episodes that might appear unrelated in the human catalog. Some variation in swarm frequency correlates with known events. Major seismic sequences, deformation episodes, and hydrothermal disturbances documented in real time. Some does not have obvious correlates in the existing record. One specific scientific question the new catalog addresses is the statistical relationship between small earthquake swarms and subsequent larger events or hydrothermal explosions. With 86-76 events to analyze, the Yellowstone swarm catalog is now large and to do meaningful statistics on these relationships. Whether particular swarm patterns are predictive of particular outcomes is now a testable hypothesis rather than a speculation. This research is ongoing. The April 2026 science paper deserves careful handling, because its implications are both significant and easy to misrepresent. The paper does not conclude that Yellowstone's volcanic system is more dangerous than previously thought. It does not conclude that a supereruption is more likely. What it concludes is that the standard account of where Yellowstone's magma comes from is well supported by the most comprehensive three-dimensional mantle model yet constructed. The central finding, the mantle wind, driven by Farallon plate subduction, needs some explanation. The Farallon plate was an ancient oceanic plate that began subducting beneath North America roughly 200 million years ago, and has been doing so continuously since, with different portions of the plate descending at different times. Its remnants now lie deep beneath Central and Eastern North America. As these remnants continue to sink, they drag the overlying mantle material in an eastward direction, a slow horizontal flow of hot rock through the mantle, which Cow et al. Call the mantle wind. This flow carries hot asthenospheric material toward the Yellowstone region from the west and south. When this material encounters the thick, cold lithosphere beneath the Rocky Mountain region, it cannot simply continue flowing horizontally, it is blocked and forced downward. The downward pull extends the overlying crust, creating conditions for decompression melting. The hot asthenospheric rock, suddenly under less pressure, partially melts, even though its temperature has not increased. This melt rises rough, a tilted plumbing system, tilting southwest because that is where the asthenospheric flow is coming from, and accumulates in crustal magma reservoirs that are well documented by seismic imaging. The paper's title, Tectonic Origin, captures the essential point. The driving force of Yellowstone's magmatic system, in this model, is not the internal heat of the deep earth rising as a plume, but the mechanical and thermal consequences of ancient plate subduction still playing out in the mantle. Why does this matter? The deep plume model and the shallow asthenosphere model produce different predictions about specific aspects of Yellowstone's behavior. A deep plume is relatively self-contained and steady. Its heat comes from near the core mantle boundary and is largely independent of regional tectonics. A shallow, asthenospheric system, driven by Firehole remnants, is more episodic and more sensitive to changes in the configuration of those remnants as they continue to sink and fragment over geological time. The timescales and patterns of magma supply to Yellowstone's surface reservoirs may be more variable than the deep plume model predicted. The July 2025 to January 2026 North Caldera Rim uplift episode is, in some ways, the most directly observatory relevant of the three new findings, because it is happening in the monitoring record right now. Beginning in July 2025, GPS stations monitoring the North Caldera Rim recorded uplift in the area to the south of Norris Geyser Basin, the same location where uplift had occurred during the 1996 to 2004 episode. The uplift reached a few centimeters at its maximum and then stopped by mid-January 2026. The historical context matters. The 1996 to 2004 uplift was interpreted, retrospectively, as accumulation of hydrothermal fluids in the shallow crust beneath the Norris Geyser Basin region. Those fluids eventually drove a period of thermal ground disturbance at Norris in 2003. The area continued to show deformation into 2013 and 2014, when uplift near Norris Geyser Basin occurred at rates of up to 15 centimeters per year, one of the fastest deformation rates ever recorded at Yellowstone. That episode ended with the M4.8 earthquake of March 2014, the largest since 1975, which switched the deformation from uplift to rapid subsidence. The July 2025 episode shares the same geographic location. As Firehole noted in Caldera Chronicles, a swarm occurred directly on top of the center of uplift in November 2025. Echoing the link between deformation and seismicity seen in the previous episode. Then, the uplift stopped in January 2026, without the subsidence that completed the previous patterns. As of the most recent USGS update for May 2026, there has been no uplift or subsidence of the Yellowstone caldera or North Caldera Rim since January 2026. The ground is currently stable, but the caldera had been subsiding at a rate of about an inch per year since 2015, and that long-term subsidence has paused. The first winter since 2015-2016, with no caldera subsidence, which the USGS noted in its April 2026 report, is a subtle but observable change in behavior whose cause and future trajectory are not clear. What is not explained is whether the pause in subsidence is temporary, whether it represents the beginning of a new uplift phase, or whether the system has simply transitioned to a different deformation state. And Firehole was explicit about the limits of sea-errant knowledge. At this point, there is no way of knowing what will come of this current deformation episode. There are three frames for understanding what the 2025 to 2026 Yellowstone findings collectively represent. The first frame is methodological progress. The three findings are primarily a story about science getting better. Machine learning can now find earthquakes that human analysis missed. Geodynamic modeling at the scale of the Western North American Mantle Sea, and now resolve structure well enough to challenge the deep plume model. GPS monitoring is sensitive enough and has run long enough to detect subtle deformation episodes. None of these advances indicate that Yellowstone's volcanic hazard has increased. They indicate that the tools for studying Yellowstone have improved, and the more detailed picture they provide has both confirmed some aspects of the standard model and identified specific places where the model is incomplete. The second frame is epistemic humility. And in this view, The significance of the three findings is not their specific content, but their cumulative message. A system that has been closely monitored for decades is less well understood than the monitoring SUGIS, TED. The AI earthquake catalog shows that the seismic picture was incomplete. The magma origin paper shows that the driving mechanism model was at least partially wrong. The North Caldera Rim deformation shows that specific observations do not fit historic AL precedent cleanly. Each of these is manageable individually. Together, they suggest that uncertainty about this system is larger than the standard account implied. The third frame is the most practically relevant for hazard management. The three findings together require that the Yellowstone Volcano Observatory review specific aspects of its hazard assessment framework in light of the new science, not to change the alert level, which would be unwarranted given the current monitoring data, but to ensure that the thresholds, baselines, and predictive models embedded in the monitoring program are consistent with the new understanding of the system. Are the swarm detectio N thresholds calibrated to the new, denser earthquake catalog, or to the old, sparser one? Is the monitoring strategy for the North Caldera Rim area adequate to detect the continuation of the July 2025 deformation episode, if it resumes? What does the new MA-GMA origin model imply about which geochemical signals should be prioritized in the gas monitoring program? These are technical questions without dramatic answers. They are the questions that the people responsible for monitoring Yellowstone are working through in the months following the publication of the three findings. What none of the three frames supports is the conclusion that Yellowstone is building toward an eruption. The monitoring data does not support this. The USGS assessment does not support this. The findings themselves do not support this. What they do support is the conclusion that Yellowstone is more seismically active at small scales than the working catalog showed, that its driving mechanism is better described by a shallow tectonic model than a deep plume model, and that its deformation behavior in the current episode does not follow the historical pattern cleanly. In a system of this scale and this significance, those three things together are worth understanding precisely. One of the three new findings is fundamentally about Yellowstone's hydrothermal system, and it is worth spending a moment on what hydrothermal explosions actually are and why they represent a genuinely different category of hazard from volcanic eruptions. A hydrothermal explosion is not a volcanic eruption. It does not involve magma reaching the surface, it involves water. Beneath Yellowstone's surface, groundwater heated by the magmatic system below circulates through a network of cracks and pores in the rock. At certain locations, including Black Diamond Pool in Biscuit Basin, this water exists very close to its boiling point at depth. The pressure of the overlying water and rock is what keeps it liquid. If that pressure is released suddenly, by a change in groundwater levels, by an earthquake that opens a new pathway, or by some other trigger, the water flashes instant lie to steam. Steam occupies approximately 1/700 times the volume of liquid water at the same temperature. That expansion is explosive, and it drives whatever overlies the water, rock, soil, mud, violently upward. The result is an explosion that looks dramatic, but is fundamentally different from a volcanic eruption in terms of its driving mechanism and its hazard zone. The July 2024 Biscuit Basin explosion ejected a plume 120 to 180 meters high through boulders more than a meter in diameter across the area and destroyed the boardwalk. It had no precursors detectable by the monitoring system in place at the time. It was not preceded by elevated seismicity, anomalous ground deformation, or changes in gas output. It simply happened. This is the specific character of the hydrothermal explosion hazard. It operates on timescales and through mechanisms that are largely invisible to the monitoring systems designed to detect volcanic eruption precursors. A volcanic eruption requires magma to ascend through the crust, a process that takes time and leaves seismic, geodetic, and geochemical signatures along the way. A hydrothermal explosion requires only a rapid pressure change in a water-saturated rock volume, which can occur on timescales of minutes to hours without leaving clear precursors in monitoring data recorded kilometers away. This is why the June 13, 2026 event, which occurred within 100 meters of the newly installed monitoring station, is scientifically significant beyond just documenting another explosion. It is the first explosion in Yellowstone history to occur close in USGS to a monitoring station that detailed pre-explosion seismic and infrasound data may have been recorded. If analysis of that data reveals any precursory signal, even a small one, even one that would have been too ambiguous to act on without the benefit of hindsight, it would be the first observational evidence for hydrothermal explosion precursors at Yellowstone. That is a potential breakthrough for a hazard that has, until now, resisted all attempts at prediction. The USGS Caldera Chronicles article describing the June 13 event, authored by Jefferson Hungerford, Kiernan Falls Donahue, Michael Poland, Jamie Farrell, and colleagues, explicitly names this opportunity. No hydrothermal explosion has ever occurred this close to a monitoring station, and the June 13, 2026 explosion thus offers an unprecedented opportunity to better understand this critical hazard in Yellowstone National Park and perhaps learn more about their potential warning signs. That language, unprecedented opportunity, reflects genuine scientific excitement, not alarm. The Biscuit Basin Monitoring Network was installed precisely because scientists recognized that Black Diamond Pool, after the 2024 event, was the most active, and most closely watched hydrothermal explosion site in the park's history. The June 13, 2026 event delivered exactly the kind of data that the network was designed to collect. Let's come back to where we started. 3 scientific findings, published within 12 months of each other, each from a different direction, each finding something that the standard model of Yellowstone did not capture. A machine learning catalog that expanded the earthquake inventory tenfold LD and revealed a system of pressured fluid compartments breaking through permeability seals in episodic bursts. A new mantle model that relocated the magma's origin from a deep plume to a shallow asthenospheric source, driven by horizontal flow from ancient T-Farallon plate subduction. A deformation episode that mirrors a historical precedent but does not follow it exactly, ending without the subsidence that would have completed the pattern. And on June 13, 2026, at 5:09 a.m. Mountain Daylight Time, the fifth hydrothermal explosion of the year at Biscuit Basin, not from Black Diamond Pool itself, but from the barren ground north of it, creating new fractures, 3 sets of newly formed vents, and, by June 14 to 16, a new pool of vigorously boiling water that was spouting 6 to 9 meters into the air by June 18. Captured in full by the monitoring network installed after the first explosion at this location in July 2024. The USGS alert level is normal. The system is at background levels, no precursors of volcanic eruption have been detected, and 3 of the most important pieces of Yellowstone science, published in the past year, have each found that the standard model of the system was incomplete in specific identified ways. Both of these things are true simultaneously. Managing the tension between them, communicating clearly about what is known and what is uncertain. is what the YVO does every month in its public updates. What the three new findings have done is make the succinct description of what is uncertain somewhat longer. What the headlines missed. Yellowstone coverage falls into two consistent failure modes: the doomsday version, the dismissal version. The 2025 to 2026 findings have been covered poorly in both directions. Several outlets covered the AI earthquake catalog with the obvious framing: 86,000 earthquakes hidden beneath Yellowstone, as a scary number without context. 86,276 earthquakes over 15 years is approximately 5,750 per year, compared to the 500 in the standard catalog. Yes, this is larger. No, it does not mean the system suddenly became more active. The earthquakes were always happening. Better analysis found them. And the finding is not simply that there are more earthquakes. It is that the pattern of those earthquakes reveals a specific physical mechanism: episodic seal breaking in a pressured hydrothermal system. That is the scientific content, and it received almost no coverage. The April 2026 magma origin paper in Science was covered in some specialist outlets and essentially ignored in popular media. A major revision to the foundational model of what drives one of the most closely watched volcanic systems in the world, published in one of the two highest-tier general science journals, should have received substantially more attention. The mantle wind mechanism, horizontal asthenospheric flow, driven by the ancient Farallon plate subduction, pushing magma source material toward Yellowstone, is a genuinely novel physical picture that changes how the system is understood to work. The North Caldera Rim uplift episode received coverage primarily through USGS Caldera Chronicles articles. The specific combination of uplift in a historically sensitive location, associated seismic swarm directly on the uplift center, and anomalous termination without expected subsidence was not widely communicated as an integrated observation. Here are the specific things that most coverage missed. The methodological significance of the AI finding. The catalog expansion is not primarily a finding about Yellowstone being more dangerous. It is a finding about what machine learning enables in seismic analysis of any volcanically and hydrothermally active system. The same approach can and will be applied to other volcanic systems worldwide, potentially revealing similarly expanded earthquake catalogs at systems whose hazard assessments are based on similarly incomplete historical records. The Yellowstone finding is a methodological landmark, not just a Yellowstone finding. The specific physical mechanism it revealed, pressured fluid compartments breaking through permeability seals, is a new understanding of how hydrothermal systems generate seismicity has implications beyond Yellowstone. The mantle wind mechanism. The shift from deep plume to shallow asthenosphere origin does not simply relocate where the magma comes from. It changes the predicted dynamics of magma supply in a specific way. A shallow, asthenospheric source, driven by Farallon end plate remnants, is more episodic and more dependent on the ongoing evolution of those remnants as they continue to sink and fragment. The long-term predictability of Yellowstone's magmatic behavior, including the timescale between major eruptive episodes, may be different from what the deep plume model predicted. This is the implication that needs working out. The deformation anomaly. The fact that the North Caldera Rim uplift stopped without subsidence, the first winter since 2015-2016 with no caldera subsidence, has not been explained. Scientists have explicitly said they do not know where this deformat ion episode leads. This is a genuine and acknowledged uncertainty in the monitoring record, and it receives almost no coverage outside the USGS own public communications. The Biscuit Basin Monitoring Opportunity. The June 13, 2026, Caldera Chronicles article, written by Jefferson Hungerford, Michael Poland, Jamie Farrell, and colleagues, explicitly described the event as an unprecedented opportunity to better understand Thi's critical hazard in Yellowstone National Park and perhaps learn more about their potential warning signs. This is not alarm. It is scientists recognizing that they have, for the first time, a hydrothermal explosion event that occurred within 100 meters of an active monitoring station, meaning that if there were seismic or infrasound precursors, there is a good chance they were recorded. No hydrothermal explosion has ever occurred this close to a monitoring station before. The latest data, and what IT shifts the most recent USGS Yellowstone Volcano Observatory monthly update, covering May 2026, describes a system at background levels, 45 earthquakes located in the park during May, the largest a magnitude 2.0, no swarms identified. No significant ground deformation since January 2026. This is the baseline against which the three new findings must be understood. The system is not showing elevated volcanic precursor signals. The AI catalog finding, the magma origin revision, and the North Caldera Rim deformation episode are not manifest in current monitoring data as anything requiring a change in alert level. What the May 2026 update also notes, specifically, is that the Echinus geyser in Norris Geyser Basin reactivated in February 2026 after several years of dormancy. Echinus is a rare acidic geyser, one of the very few in Yellowstone, and its activity patterns have historically been related to the thermal state of the Norris Geyser Basin hydrothermal system. Its reactivation in the same period as the North Caldera Rim deformation episode is noted by YVO scientists without a clear interpretation. The Biscuit Basin situation continues to evolve. The June 13 explosion, the fifth hydrothermal explosion at this location in 2026, occurred at 5:09 a.m. MDT and was captured by the monitoring camera. 3 new vent groups formed, including an 18.5-meter fissure filled with near-boiling water. A new pool formed by collapse between June 14 and 16, and by June 18, it was spouting boiling water 6 to 9 meters into the air in intermittent geyser-like episodes. As of this recording, the monitoring network at Biscuit Basin is actively collecting seismic, infrasound, and temperature data from the site, reviewing whether any precursors to the June 13 event appear in the record, which would be scientifically unprecedented. The April 2026 science paper on magma origin has already generated scientific discussion, with researchers in the Yellowstone and broader hotspot science community assessing its implications for existing models. This discussion is ongoing and has not yet produced a community consensus on how the new finding should change specific aspects of Yellowstone science. And the machine learning earthquake catalog from July 2025 has, since its publication, been available for other researchers to use in studies of Yellowstone's hydrothermal and seismic dynamics. Follow-up studies investigating swarm patterns, fluid movement, and the relationship between small earthquakes and hydrothermal features are in progress at multiple institutions. What this means for the future, the practical implications of the 3 new findings for Yellowstone science and monitoring fall into several categories. For the seismic monitoring program, the AI earthquake catalog creates a new baseline. Future seismic analysis at Yellowstone will likely incorporate machine learning detection as a standard part of the catalog production process, expanding the routine detection threshold below what human analysis has historically captured. This will progressively improve the resolution of the seismic picture, and may allow the detection of subtle patterns in swarm behavior that are currently invisible in the real-time catalog G. The specific physical mechanism identified by Flores, Lai et al. Pressured fluid compartments releasing in episodic injections provides a more detailed framework for interpreting swarm sequences as they occur in real time. For the hazard assessment framework, the magma origin revision and the North Caldera Rim deformation episode both argue for reviewing whether specific thresholds and baselines in the assessment are calibrated to the correct model. The YVO has been explicit in its Caldera Chronicles articles about the uncertainty surrounding the current deformation state, and the monitoring program has been adjusted to give enhanced attention to the North Caldera Rim area. For the hydrothermal explosion hazard specifically, the activity at Biscuit Basin in 2026 has provided the richest dataset ever collected on a specific hydrothermal explosion site in Yellowstone. The monitoring infrastructure installed since July 2024 is providing real-time data on explosion events, their precursors, their physical consequences, and the subsequent evolution of the hydrothermal system at that location. Whether that data will eventually allow prediction of future events is an open question. The data being collected right now, potentially including the first ever recording of precursors to a hydrothermal explosion at close range, may eventually change what we know about how these events develop. The broader lesson, applicable to volcanic monitoring worldwide, is the one demonstrated by the AI earthquake catalog. Historical seismic datasets at volcanic systems, analyzed with pre-machine learning methods, likely contain tens of thousands to hundreds of thousands of previously undetected small earthquakes. Applying modern machine learning methods to these archives, at Yellowstone and elsewhere, is likely to produce systematic revisions to the seismic picture of volcanic systems, globally, with implications for hazard assessments, wherever those assessments depend on the completeness of the seismic record. Here is what the 2025 to 2026 Yellowstone findings actually reveal, at the deepest level. For decades, the monitoring of Yellowstone has been built on a specific, implicit assumption that the most closely watched geological system in the United States is well enough understood that the monitoring can be calibrated to the expected behavior of a system whose driving mechanism and activity level are known with reasonable confidence. The three findings together challenge this assumption at three distinct levels. At the level of what is happening now, the AI catalog finding shows that the seismic activity of the system is 10 times more intense at small scales than the monitoring catalog captured, and that the mechanism driving this activity, episodic seal break-in G in pressured hydrothermal compartments, is more complex than the previous picture implied. At the level of what drives the system, the mantle model finding shows that the primary energy and material source is not where the standard model located it, not a deep plume from near the core mantle boundary, but shallow asthenospheric material redirect-ed toward Yellowstone by the horizontal flow consequences of ancient Farallon plate subduction. A geodynamic picture that is both more surprising and more tectonically interconnected than the classical hotspot story. At the level of what the monitoring is observing in the current deformation record, the North Caldera Rim finding shows that the current behavior does not fit the historical precedent cleanly, and that the is, with honesty that deserves acknowledgement, describing the situation as one with no clear prediction. These three findings do not add up to an imminent volcanic eruption. They add up to a revised description of a system that is more active, more complex, and less predictable in its specific behavior than the pre-2025 model described. Scientists who work on volcanic hazard assessment for a living know that the quality of a hazard assessment is only as good as the quality of the model it is based on. When 3 independent lines of research each find that the model is incomplete, the appropriate response is not alarm. It is careful, sustained, enhanced attention, exactly the kind of attention that the YVO has been giving Yellowstone since these findings appeared, and that its monthly Caldera Chronicles articles reflect in the form of HON-EST statements about what is observed, what is uncertain, and what does not yet have a clear interpretation. There is also a broader point about how science advances, which this moment at Yellowstone illustrates particularly well. The 3 findings did not come from a single alarming observation. The AI catalog came from applying new computational methods to archived data. The mantle model came from integrating multiple types of geophysical observations into a unified physical framework. The deformation observation came from GPS stations that have been running for years, accumulating a record long enough to identify when current behavior deviates from historical norms. In each case, the surprise came not from an emergency but from the accumulation of better data and better analysis. This is how science is supposed to work. Not a series of crises, but a continuous process of building more accurate descriptions of complex systems. The uncomfortable corollary of this is that a more accurate description does not always mean simpler description. Yellowstone in June 2026 is a more complicated system than Yellowstone in 2020. Not because the system itself has changed, but because the science of it has improved. The 86, 276 earthquakes were always happening, the Farallon-driven mantle wind was always flowing, the permeability seals were always breaking. What has changed is the resolution with which scientists can see and describe these processes. And higher resolution, almost always, reveals more complexity than lower resolution suggested. That recognition, and the careful scientific work that follows from it, is what responsible volcanic monitoring looks like when a well-watched system produces genuine surprises. There is one more thread in this story worth following. The Yellowstone hotspot, whether driven from the deep mantle, as the traditional model describes, or from shallow asthenospheric flow, as the April 2026 paper suggests, has been leaving a trail across the North American plate for approximately 17 million years. That trail, the Snake River Plain, runs from Nevada and Oregon through Idaho to Wyoming, a chain of ancient calderas that marks the path of the hotspot relative to the moving plate. The new magma origin model changes how we understand that trail. If the eastward mantle wind from Farallon plate subduction is what carries asthenospheric material toward the volcanic system, then the track of Yellowstone across the continent is not just the record of a stationary heat source underneath a moving plate. It is also the record of how the Farallon remnants have been evolving in the mantle over millions of years, reshaping the flow of hot rock toward the surface as they sink and fragment. That story, Yellowstone as one frame in a much longer geodynamic film involving some of the largest plate tectonic events in North American geological history, is one with a new chapter from 2026. That is a story for another time. We started with a hydrothermal explosion at Biscuit Basin, June 13, 2026. At 5:09 a.m., monitoring equipment recorded seismic energy and infrasound from north of Black Diamond Pool. A steam plume jetted from the ground. 3 new vent groups formed. The Firehole River turned milky gray for hours. A new pool formed by collapse in the following days, and by June 18, it was spouting boiling water 6 to 9 meters into the air. all of it captured by the monitoring network that was installed because of what happened at the same location in July. Then, we followed 3 scientific developments that have, in the past 12 months, each from a different direction, found something at Yellowstone that the standard model did not account for. 276 earthquakes in 15 years of seismic data, 10 times more than human analysis found, revealing a hydrothermal system of pressured fluid compartments releasing in episodic bursts through broken permeability seals. A magma origin shallower and more tectonically controlled than the deep plume model described, driven by a horizontal mantle wind from the subducting remnants of the ancient Farallon plate, a North Caldera Rim deformation episode that ended without the expected subsidence, and whose future trajectory us scientists describe explicitly and honestly as unclear. The USGS alert level is normal. The system is at background levels. No precursors of volcanic eruption have been detected. And the 3 most important pieces of new Yellowstone science in the past year have each found that the model of the system that the monitoring was calibrated to needs revision. Both of these things are true. Holding both of them accurately, without collapsing one into the other, is what understanding Yellowstone in June 2026 actually requires. The North Caldera Rim deformation episode, which began July 2025 and stopped in January 2026 without the expected subsidence, remains without a clear interpretation. Whether it will resume, or was a transient that is now complete, is not yet known. The associated pause in the decade-long caldera subsidence trend is also unexplained. This is the first winter since 2015-2016 in which the caldera has not subsided, and the geological reason for this pause has not been identified. The deformation record going forward, whether subsidence resumes, whether new uplift begins, or whether the system remains in a new stable configuration, will be one of the most watched aspects of Yellowstone monitoring in the coming months. The relationship between the AI expanded earthquake catalog and the hydrothermal explosion hazard at specific Yellowstone sites has not yet been fully characterized. Whether particular swarm patterns in the new catalog, specifically, the episodic seal-breaking sequences identified by Flores et al., are statistically associated with subsequent hydrothermal explosions, is a research question being actively investigated. If a statistical relationship is found, it would create the possibility of using swarm catalogs as leading indicators of hydrothermal explosion risk at specific sites, a form of early warning that does not currently exist for this hazard. The implications of the shallow asthenospheric magma origin model for Yellowstone's long-term volcanic behavior, including the predicted timescale between major eruptive episodes and the response of the system to changes in regional tectonics, have not yet been fully worked out by the scientific community. The community discussion, prompted by the Cow et al. Paper, is ongoing, and the process of integrating its findings into the broader framework of Yellowstone volcanic science will take years. The ongoing eruptive activity at Black Diamond Pool in Biscuit Basin, 5 events in 2026, represents a change in documented behavior at that specific location. Whether the new monitoring data contains precursors to the June 13 explosion is being actively reviewed. Whether the frequency of explosions at this location represents a new stable activity pattern or a transitional state is not yet established. And the question of whether the seismic monitoring program's real-time detection thresholds and swarm identification criteria should be updated to reflect the 10 times larger earthquake population revealed by the AI analysis has not been publicly resolved. Incorporating machine learning detection into the routine operational monitoring pipeline, rather than as a retrospective research tool, would be a significant technical undertaking, but one that the Flores et al. Paper makes the scientific case for. First, the completeness of a monitoring record depends on the methods used to analyze it. The human-analyzed Yellowstone seismic catalog captured a fraction of the earthquakes that were actually occurring. Machine learning expanded it tenfold and revealed a physical mechanism, episodic fluid injection through broken permeability seals, that was invisible in the sparser record. Any hazard assessment based on a monitoring record that is itself incomplete inherits that incompleteness. The Yellowstone finding is a specific case of a general principle that applies to every volcanic and hydrothermal system monitored worldwide. Second, foundational scientific models of complex systems can be wrong in consequential ways without any specific monitoring signal indicating a problem. The deep plume model of Yellowstone has been the foundation of its volcanology for decades. The April 2026 science paper challenges it not because of any alarming new monitoring observation, but because of a more comprehensive model of the mantle. The model revision came from better science, not from an escalating hazard signal. This is an important reminder that scientific understanding advances through new analytical frameworks, not only through new observations. Third, honest scientific communication about uncertainty is not the same as alarm. The USGS language in its Caldera Chronicles articles, noting explicitly that there is no way of knowing what will come of the current deformation episode, is an honest description of the observational situation. This honesty is not a warning of danger. It is an accurate characterization of what is and is not known. The appropriate response is not anxiety, but continued monitoring, and the kind of scientific attention that eventually resolves uncertainty. Fourth, the hydrothermal explosion hazard at Yellowstone is real, ongoing, and poorly understood in terms of short-term prediction. The July 2024 Biscuit Basin explosion had no detected precursors. The 5 subsequent explosions in 2026 are being monitored in unprecedented detail, including, for the first time, an event that occurred within 100 meters of a monitoring station. Whether this detail will eventually allow prediction of future events is an open question with practical safety implications for millions of park visitors annually. Fifth, a system being less well understood than previously believed is not the same as a system being more dangerous than previously believed. The 3 new Yellowstone findings have made the system's description more accurate and its uncertainty more explicit. They have not changed the volcanic hazard assessment, but they have changed what that assessment is built on, and the process of updating the assessment to reflect the new science, more swarm resolution, a revised driving mechanism, an unexplained deformation episode, is the responsible next step. If machine learning can find 10 times more earthquakes in 15 years of Yellowstone data than human analysts did, and if those additional earthquakes reveal a specific physical mechanism of episodic seal breaking in pressured hydrothermal compartments, does this imply about the completeness of the seismic records used to assess volcanic hazard at other monitored systems worldwide? How many volcanic systems are being managed based on catalogs that contain only a fraction of the earthquakes that have truly occurred? The USGS is explicit that it cannot predict what the current North Caldera Rim deformation episode will lead to. This is honest science. But how should the public relate to honest statements of uncertainty from agencies responsible for managing geological hazards? Is there a way to communicate genuine uncertainty without producing either alarm or dismissal? And what would it take for news coverage to report, "Scientists don't know what will happen next," as a scientifically meaningful statement rather than either a frightening revelation or a reassuring non-event? And, on the broadest level, the April 2026 mantle model says Yellowstone's magma comes from shallower sources driven by ancient plate subduction, and the July 2025 earthquake catalog says the system is 10 times more seismically active at small scales than the working catalog showed, through a more complex mechanism than previously described. Both findings make the system more interesting and more uncertain simultaneously. The question of whether that makes it more frightening or more fascinating is worth CTing with. What changes in how you think about geological systems when the honest answer to "how does this work" is "better than before, but not as well as we thought"? If this one stayed with you, let us know which development landed hardest. The AI Earthquake Catalog. 86, 276 events in 15 years, 10 times more than human analysis found, revealing a hydrothermal system of pressured compartments releasing in episodic bursts. The April 2026 magma origin finding. A mantle wind from ancient Farallon plate subduction, driving Yellowstone's power from shallower sources than decades of standard models described. The North Caldera Rim deformation that stopped without the expected subsidence, leaving us scientists explicitly saying the outcome is unclear. Or, the June 13, 2026 hydrothermal explosion at Biscuit Basin, the fifth of the year, new fractures, new vents, a new pool spouting 6 to 9 meters on June 18. Everything are dead in real time by monitoring installed because of what happened in July 2024, and potentially containing the first ever recorded precursors to a hydrothermal explosion. And if you want more of this, Yellowstone and other geological systems told with actual science, including the parts that are genuinely uncertain, subscribe to Galaxy Pulse. And we will see you in the next one. The is alert level is normal. 3 scientific findings in 12 months have each found something that the standard model of this system did not capture. The system is at background levels. It is also more seismically active than the catalog showed, driven by shallower and more complex sources than the model described, and currently showing a deformation pattern that does not follow historical precedent cleanly. All of these things are true. That is what it looks like when good science is done honestly on a complicated system. That is Yellowstone in June 2026. A note on what Yellowstone represents in the broader landscape of volcanic monitoring. The 3 findings from 2025 and 2026 are specifically about Yellowstone, but their implications radiate outward to volcanic monitoring worldwide in ways that are worth making explicit. Yellowstone is the best monitored volcanic system in the United States and among the best monitored in the world. It has an observatory dedicated exclusively to it, 50 seismometers, continuous GPS, gas sensors, satellite thermal monitoring, and a team of scientists who publish monthly reports on every observable parameter of the system. If the standard seismic catalog for a system, this well-monitored captures only 1/10 of the actual earthquakes occurring. The implications for less well-monitored systems are sobering. There are hundreds of active and potentially active volcanic systems worldwide. Most of them are monitored with far fewer instruments than Yellowstone. Many are monitored only through regional seismic networks, with no local instruments, no gas sensors, no continuous GPS. Their seismic catalogs have been compiled by human analysts applying the same detection methods, trained human review of waveform data, that the Flores et al. Paper demonstrated captures only a fraction of actual seismicity at Yellowstone. If Yellowstone's seismic catalog underrepresented actual seismicity by a factor of 10, it is plausible that the catalogs for less well-monitored systems underrepresent actual seismicity by larger factors. The hazard assessments for these systems, based on those incomplete catalogs, inherit that incompleteness. The specific physical mechanism revealed by the Flores et al. Analysis, episodic seal breaking in pressured hydrothermal compartments, may be a general feature of volcanic hydrothermal systems that is currently invisible at most monitored systems, because the catalogs are too sparse to reveal it. This is the methodological significance of the Yellowstone AI catalog result that most coverage missed. It is not a finding about Yellowstone specifically. It is a finding about what machine learning reveals when applied to any volcanically active systems, archived seismic data. The implication is that applying the same approach to archived data from other well-instrumented volcanic systems, Mount Rainier, Mauna Loa, the Canary Islands, Mount Erebus, the Aleutians, Santorini, could produce similarly expand-dead catalogs with similarly rich physical information. The Yellowstone paper is the proof of concept. The scientific community will now apply the method more broadly. Similarly, the Cow et al. Magma origin finding has implications beyond Yellowstone. The paper's authors explicitly note that the mechanism they identified, asthenospheric melt generated by tectonic extension and delivered to the surface through a tilted T-translithospheric pathway, may apply to other large volcanic regions. If shallow asthenospheric sources controlled by regional tectonics are a more general mechanism for large volcanic systems than the deep plume model assumed, the driving mechanisms of her volcanic provinces may need to be reconsidered as well. The lessons of the Yellowstone mantle model revision will eventually propagate to how scientists think about magmatic systems in general. And the hydrothermal explosion monitoring work at Biscuit Basin, the unprecedented opportunity described in the June 2026 Caldera Chronicles article, has the potential to advance the general science of hydrothermal explosion prediction in ways that benefit not just Yellowstone, but any location where hydrothermal explosions pose a hazard, including Rotorua in New Zealand, the Werrikei geothermal field, and the many other places worldwide where hydrothermal activity overlaps with human presence. Yellowstone, in 2025 and 2026, is producing a set of scientific advances that matter beyond Yellowstone. The system is giving the science community better methods, a revised physical picture, and an unprecedented monitoring dataset. That is what a well-observed system can do when it is approached with the right tools and the right questions. What it means to watch a system surprise you. There is a form of scientific experience that is rarely discussed in public science communication, but is central to how researchers actually feel about their work. The experience of a well-studied system doing something you did not expect. For the scientists at the Yellowstone Volcano Observatory, the past 12 months have contained 3 separate instances of this experience. The AI earthquake catalog found the seismic activity they thought they understood to be 10 times more extensive and physically more complex than their working description. The mantle model found the driving mechanism they thought they understood to be operating from a different source through a different process. The GPS record found the deformation behavior they understood to be deviating from the historical pattern in a way that does not yet have a clear explanation. None of these experiences indicate that Yellowstone is about to do something dangerous, but each of them is the experience of recognizing, through data and analysis, that the description you have been working with was incomplete in a specific, identified WI. And this experience, being surprised by a system you have been watching carefully, is what good science produces when it is working. It is not a failure of monitoring or analysis. It is the signal that the monitoring and analysis have improved to the point where the gaps in the previous description have become visible. The YVO scientists could have responded to these surprises by hedging, by downplaying the discrepancies between new findings and standard models, by emphasizing that the alert level has not changed and leaving the rest unexplained. Instead, the Caldera CHR Onacles articles have been unusually direct about the limits of current understanding. No way of knowing what will come of this unprecedented opportunity. The outcome is unclear. This directness is not an accident. It is a deliberate choice to communicate honestly about a system that is producing observations that do not fit the previous model cleanly, while also being clear that honesty about uncertainty is not equivalent to a warning of danger. What gives volcanologists pause about Yellowstone in 2026 is not imminent eruption. It is the recognition that the system is telling them things that their current model does not fully explain. And in science, when a well-monitored system starts telling you things your model does not explain, the correct response is exactly what the YVO is doing: more monitoring, better methods, honest acknowledgement of what is uncertain, and continued attention to the data. That is what Yellowstone in June 2026 looks like: not alarming, not routine, something in between. A complicated system producing genuine scientific surprises, being observed by scientists who are doing exactly what they should be doing with those surprises.